Hello everyone, and welcome to this video on obtaining the graph of the inverse function from the graph of a function. Alright, so in this video we're going to be given, well, first off I'm going to go over how the graph of a function and its inverse are related. They're actually symmetrical about the line y equals x, as we'll see. And then I'll go into an example where I'm given the graph of a one-to-one function. If you recall from previous videos, a function must be one-to-one in order for its inverse to also be a function. And remember, and see I have inverse function here. And we'll be given the graph of a one-to-one function and asked to draw the graph of the inverse function. Okay. So on my first page, I just have some graph paper here, and I just want to put a nice note about the relationship between the graph of a function and its inverse. So the graph of a function f and the graph of its inverse, f inverse with the little -1 above it, right? F inverse, are symmetric with respect to the line y equals x. So what I have here is, my x and y axes, and then here a little dashed line, dotted line, most of it, I kind of had some solid parts here, but this is the line y equals x right here. It's got 0, 0, 1, and I have every square on the x and y axis representing one unit. So you got 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, all those points, etc. There's the line y equals x. And then what I've done here, alright, I'm just going to show you a few examples with just a couple points, what happens when I draw, the inverse of those points. Remember what happens to an ordered pair in a function when you look at that same, when you take the inverse. Right? They switch, right? The coordinates switch. Values in the domain become values in the range. X values become y values, and vice versa, right? Values in the range become values in the domain, or y coordinates become x coordinates in the inverse. So I've got a few points here that are labeled with this maroon color. So suppose these are in function f. Alright, suppose these 3 points here are in the function f. So I've got -4, 3, so -4 for the x, 3 for the y, -4 input, 3 output. Got 2, 6, right? 2 input, 6 output. And this other point, 12, 6 over here, right? Just a few examples. So suppose all 3 of these points in this maroon color are in function f. Now I'm going to do in another color, so like a little aqua color, or like a greenish. The corresponding points that would be in the inverse, right, in the function f inverse. Right. Now I'm already saying that this is a bad example because this is not one-to-one. Wow. Well, anyway, the next example I'll have a one-to-one function, and the inverse will be a function. Here it won't be a function, but let me just show you how the graph of a function and its inverse, because this is still a function, right? Every input gives me one output. But the graph of a function and its inverse, even though the inverse won't be a function here, are still symmetric about the line y equals x. So like -4, 3, right? -4 for the x, 3 for y. If this isn't a function, what would the ordered pair that would be in the inverse would be, switch these, 3, -4. So 3 for the x and -4 for the y. All right, so this point down here, I'll label this, right, 3, -4. And hopefully you can see how this is actually, this point and this point are just a reflection across this line y equals x. If I turn this up this way, you see how they're like this, they're the same distance. If I was to draw a little segment connecting them, a little dotted segment, See, they form this little 90-degree, that segment forms a 90-degree angle with the line y equals x. And can you see it? The distance from this point to the line y equals x is the same as the distance from y equals x to this other point. So there's clearly a reflection across the line y equals x, right, for a point to the same, to the corresponding point in its inverse. All right. Then 2, 6. Again, if this was in a function, what would be in the inverse? 6, 2, right, to switch the coordinates. So 6, 2, this point here. Again, I'll label it 6, 2. And again, if you look at this point, 2, 6, and this point where I switch the coordinates, right, take the inverse, 6, 2, they're a reflection across this line y equals x. And again, if I turn it this way, maybe it's easier to see. Or drawing a little segment between them, or a little dotted segment, a dash because it's not supposed to be there. Between these 2 points, again, you see this segment forms a 90-degree angle with the line y equals x. And the distance from 2, 6 to the line y equals x is the same distance, well, 2 tick marks because I already used 1 tick mark, as 6, 2 to the line y equals x. All right. Definitely a reflection across the line y equals x. All right, they're symmetrical. All right. And you know what? Tell you what. Just because I messed up earlier, right? How about ignore that point? But you can see the reflection, right? Because now look, if I had a function with just these 2 points, that's 1-to-1, and doing the reflections, these 2 points, 6, 2 and 3, -4, they form a function, right? Yeah, if I had this point here and did the reflection, I'd have, I'd have 6, 12 as well, and then you'd have 2 points with an input of 6, so it wouldn't be a function. All right, so sorry, ignore the point I put up over there. I apologize. So 2, 6 to 6, 2, reflection across y equals x. -4, 3 to 3, -4, a reflection across y equals x. And really, in general, if you take any point with coordinates, say a comma b, they will reflect across the line y equals x when you take the inverse to the point b comma a. So just kind of eyeballing this here. So say up here, there's b comma a, and it should be so that if I were to connect them with a segment, right, across the line y equals x, it should be perpendicular to the line y equals x, and the distance between one point, the point on the inverse, and the line y equals x should be the same as the distance from the point on the original function and the line y equals x. Right? Again, you get this nice reflection across y equals x when you graph a function and its inverse. Switch all the coordinates. Okay. All right. So again, sorry for the little snafu there. All right. So this is what I'm doing in general when I'm asked to graph an inverse. All right. All right. So here's an example where I actually have a 1-to-1 function. So again, sorry about earlier. So below is the graph of a 1-to-1 function, right? It passes the horizontal line test. Every 2 different inputs give me 2 different outputs, right? There's no 2 inputs that give me the same output. So here's the graph of a 1-to-1 function, y equals f of x. Notice I've called it's in this light blue here, labeled f, right? Light blue f, connecting these points. So it's all these points here, these points here, these points here. And I've labeled some that's -2, 4, that's 0, 2, that's 3, 1, and that's 4, 0. All right. And what I'm asked to do is draw the graph of its inverse. Now, because this function is 1-to-1, its inverse will also be a function. Right? Because the original graph is 1-to-1, its inverse will also be a function, f inverse with the little -1 thing above it, above the f. All right, so as I did with the previous page, I'm going to plot some of these points. All right, maybe I'll zoom this in a bit. All right, so see a little more clearly. And yeah, so if these are all the points on f, let's plot some points on f inverse, and I'll do it on the same. It might be a little cluttered here. I apologize for that, but you know, it's really easy to see. I like to plot the function and its inverse on the same coordinate plane so you can see that reflection across the line y equals x. And I may even put up the line y equals x as well. So negative 2, 4 is on f, meaning that 4, negative 2, this point, is on f inverse. Right? And again, if you did that whole y, these 2 points should be a reflection across the line y equals x. 0, 2 is on f, so 2, 0, this point, is on f inverse. And again, these 2 points, 0, 2, and 2, 0, should be a reflection across the line y equals x. Alright, and 3, 1 is on f, so 1, 3, right, this point right here. There's 1, 3. So again, 1, 3, 3, 1, these should be a reflection across the line y equals x. And 4, 0 is on f, so 0, 4 is on f inverse, right, 0, 4. So again, these points, 4, 0, 0, 4, should be a reflection across the line y equals x. And then all the points in between should follow the same positions. They should follow the same pattern here. So all these points between negative 2, 4 and 0, 2 should be reflected across the line y equals x and be between 4, negative 2 and 2, 0. All right, I'll just do this in a different color, this orange color here. So all these points. So all these points I just drew are all these points, reflected across the line y equals x. And then all the points on f between 0, 2 and 3, 1, when you reflect them across y equals x, should be the points between 2, 0 and 1, 3 on f inverse. So again, connecting these 2 points in orange here. Alright, so all the points I just drew in orange are all these light blue points reflected across the line y equals x. And then finally, these points between 3, 1 and 4, 0 on f, when I reflect across y equals x, would be the points between 1, 3 and 0, 4 on f inverse, right? So connecting these two. All right, and there's the graph of f inverse, right? Little f with the -1 in orange. And look at these points. So look at these graphs. The graph of f and f inverse. I am going to put up again the graph of y equals x. All right. Let's do it in a little black color here. So that's got 0, 0 and 1, 1 and 2, 2 and 3, 3 and 4, 4. All right, it's got all these points. Do a little dotted line, y equals x. All right, and I don't need more of it because there's no piece of the graph down here, but there's y equals x. And I might as well put in more of it. All right, so there's the line y equals x. All right. And let's look at these as reflect. If I turn it this way, you can definitely see the reflection. Right? Look at all these points on f reflected across. There's the points on f inverse, and vice versa. You take points on f inverse, reflect across y equals x, you get points on f. And then all these points reflected across gives you these points. Hopefully, you can definitely see in this picture the symmetry across the line y equals x. And it's a lot easier to see on graph paper or on a calculator, but I wasn't given an actual rule. There's no equation for these functions. I was just given a graph here. So if you have graph paper, that would be wonderful. You can very easily see that reflection property going on, that reflectiveness across y equals x when you graph a function and its inverse. All right, and it's really as simple as this. If you're given a function, the graph of a function, and the points, some ordered pairs on that, just switch the order, right? Just switch the coordinates. 2, 6 becomes 6, 2, right? 0, 4 becomes 4, 0, and plot those other points, and make sure when you're done graphing a function and its inverse. Make sure, maybe even put in the line y equals x on your own, dot it in, and make certain that when you're looking at those two graphs that they do indeed look like a reflection across the line y equals x. Great. Alright, so just a little shorter message today. This is the first video where I'm going to do this. Just keep reading, keep practicing, stay persistent, stay positive, and I just know you're going to get through this. I believe in you. All right, thank you very much for watching.